走到哪？讲完这个对不对？然后到这样讲。好。Okay, please go to slide 7. Reaction order and rate law. Let me review a little bit about chapter 3. Okay, there are two parts in chapter 3. Part 1, rate law. Part 2, stoichiometry. Okay, so now we are at part 1. At part 1, the rate law. Okay, so slide 7, reaction order and rate law. So usually you will see minus RA, right? For reactant, it is minus. It is consumed, so minus. It is the target, the reactant A. R means rate, so usually you will see minus RA. It is equal to two things. The reaction rate constant, Ka, reaction rate constant. It is a function of temperature, times the function of concentration. So this function can be composed of Ca, Cb, Cc, something like that. Okay, you can fill in the blanket. You can write down this one. Just a translation of the sentence, right? The sentence rate of disappearance is equal to rate constant times function of concentrations. So we translate this sentence into a formula. So to write a rate law, you need a rate constant. You need a function of concentration. Okay, so minus RA is called the rate of disappearance of A. And what is the rate law? Rate law is an equation relates minus RA to concentration. So rate law is like this. Okay, so let's go to the next slide. Next slide. There are several points. The first one, dependence of the reaction rate on concentration of the species is determined by experimental observation. So that means if you have minus RA is equal to Ka Ca2 Cb first order. How to determine this order? This is called the order. Okay, how to determine the order by experimental observation. You do a lot of experiments and you have a lot of data. So it is like you measure minus RA, you have some concentration A, concentration B, right? So, for example, we want to find the relation. We want to find the order for Ca. So I keep Cb to be the same, right? And maybe Ca is like this. So you observe the variation of minus RA. Okay, if it is like this, then you can find the relation between minus RA and the Ca second order. So you do a lot of experiment, you have data. Every state you have data, right? You put this recipe, 4 kind of recipe, and you got a minus RA. You measure minus RA, then you got a conclusion. The relation is second order, okay? So similarly, maybe you want to find the relation with concentration B. So you keep the same concentration A. So maybe you do this, 1, 2, 3, 4, and you got a 1, 2, 3, 4. So you know they are linear dependent. So the order is 1, like this. So design the experiment, design the recipe, and you can find the order. That is the experimental observation. Okay, so second one, rate law is the product of concentration, product 相乘 of concentrations of individual reacting species, individual species A and B, and for each raised to an order, to a power. It is also the power, the order, the power. So the product of individual concentration, and for individual species, each raised to a power. So where is the example? I think example minus RA is equal to reaction rate constant times concentration A, concentration B. The power is alpha and beta. It is the general form. So you can find alpha and beta by using different recipe, like fixed CB, varying CA. You got the result. So related to these two columns, maybe you know alpha is equal to 2. Like this. Okay. The next one, order of reaction. Order of reaction is the power, alpha and beta, power to which the concentration are raised in the rate law. So the power or the order, you can state the power like for A, the power, the order, For A, the order is alpha, right? For B, the order is beta. Also, there's another indicator called the overall order. The overall order, alpha, 8, beta. So you can say the order for individual species, also the order for the overall reaction. You sum up all of the order. It is easy, right? So that is just some definition. Okay. And then I would like to talk about the rate constant, the unit for rate constant. The slide 9, the unit of rate constant. Like Ka, the unit of rate constant. It is important because if you know the unit of rate constant, you will know the order of reaction. You know the unit of rate constant, you will know the order of reaction. So in the problem, if you cannot find which is the order for the reactant, you can check the unit for Ka. So let's see how to do this. Okay, the unit for minus Ra, the unit for reaction rate is always, do you remember? Always concentration over time. Always. The definition. In a period, what's the change of concentration? That is called the reaction rate. Reaction related to concentration. Rate is related to time. So the unit for minus Ra is like this. Okay, so let me show you some different reaction with different order. For zero order, if there is a zero order reaction, zero order means N is equal to 0. N equals to 0, so what is the function? What is the function for zero order reaction? Minus Ra is equal to Ka, right? Zero order. The same, okay? For zero order reaction, okay, zero order minus Ra is equal to Ka. So what's the unit for Ka? What's the unit? The unit for Ka is the same as the unit for minus Ra, right? So you can show the unit for minus Ra, then you know the unit for Ka. Okay. So this is a unit for Ka. Sorry. Let me have one more. Ka. Yeah. It means the unit of Ka, it is concentration over time. For example, it may be more decimeter, cubic decimeter in a second. For zero order. So if you see in the problem, the unit of Ka is concentration over time, then that is zero order. How about the first order? N equals 1. N equals 1. For the first order reaction, minus Ra is equal to Ka times Ca, right? So let's write down the unit. The unit for minus Ra, still concentration over time. That is the unit for Ka. What is the unit for concentration? The unit for concentration is concentration. Right? So by calculating, you find the unit for Ka is 1 over time, like 1 over second. You can calculate the unit of Ka for second and the third order. So I don't want to write down the same process. Let me give you the answer directly, okay? You can go back to do the same thing and find the unit. Let me directly show you. I think it is simple. If you cannot get the same answer, you can email me or line me. So the unit for Ka in second order reaction, it is 到底有没有框？不如我们都不要写框。To be consistent. Okay. Just to be consistent. The unit for Ka, 1 over concentration and the time. For example, cubic decimeter over mole over second. You can calculate by yourself. Okay. Let me show you the last one. The last one is for third. Concentration square time. For example, Okay. Let me stop at a third order, but you can continue. If you are free, you can continue. So if you forget the unit for Ka, you can try to analyze it. I suggest you don't have to memorize all of the unit, but it is okay to just write down this one and check unit. So you must have to remember, if somebody give you the unit of Ka, that means somebody give you the order of reaction. Okay, the same thing. Unit of Ka means you have the order of reaction. If you cannot find the order of reaction, please try to find the unit of Ka. So next, definition. What is elementary reaction? Elementary reaction means only one step, but very seldom in real world. Very seldom for the reaction involving only one step in real world. Always more than single step. So if that is elementary reaction, you can see the word in the problem. It is an elementary reaction. If you see the elementary reaction, it is important the stoichiometric coefficient is equal to the reaction order. Stoichiometric coefficient is equal to the reaction order. So reaction order is very important to determine the rate law, right? One part of rate law is Ka. The other part of rate law is concentration. And the order is part of concentration term. So if you see this one, the problem is defined as a simple problem. You can just take a look for stoichiometric coefficient. It is the same as reaction order. So it's like the coefficient for A, for B, for C, that is the order in the rate law. The other definition, like elementary reaction, there are two words, follows and, right? Follows an elementary reaction. Okay, it is like follows and like pseudo. Pseudo, the Chinese meaning 类似或是你就是也是类似。So it is like elementary reaction, but it is not. Actually, it is not elementary reaction, but it is similar. It is like the elementary reaction. So for this word, don't pronounce P, okay? Pseudo. Okay, so how to say what is follows an elementary reaction? First one, the reaction. Okay, there are more than one reaction. Because there are more than one, so it is not elementary, right? Actually, it is not elementary. But what is the meaning for follows and or pseudo? Actually, it is not elementary, but the performance, the appearance is like. So the second one, the stoichiometric coefficient, is equal to the reaction order. You have these words in your handout, right? So I just want to emphasize. Okay, so you can see the second one. Second one is the same. Second one is the same, but the first one is not the same. So elementary means a single reaction. But this one is not a single reaction, but the appearance is like elementary reaction. So if you see elementary reaction or follows an elementary reaction, you can use this property. So I mean, if you see a chemical reaction like this, you can just use the coefficient to be the order. Okay? There are some examples in slide 10. You can take a look for this example. Just for your references, like first order, second order. The left-hand side, I think left-hand side They are all elementary reaction. Okay, you can see the third, C, non-elementary laws. So there are several expressions for the rate law. How to get a rate law from experimental observation, from experiment. So you can check paper. You can check others' experiment result to find the rate law, or do it by yourself. Design several recipes. Different recipe will give you different orders for the reactant. Okay, so let's go to slide 11. Let's talk about the non-elementary laws. For non-elementary laws, you only have to, it is necessary to do some experiments and find the rate law. So first kind is homogeneous reaction. Homogeneous reaction means a single phase, right? Single phase. The reactant, the product are both in gas phase, liquid phase, or solid phase. So that is homogeneous, only one phase. The first one, the overall order don't have to be an integer. So it can be 3/2. Oh, let me show you the rate law for this example. It's just for your reference. So this one is non-elementary rate law. This one, non-elementary rate law. So you cannot use the coefficient to write down the rate law. So this rate law is from the experiments. For your reference, okay? The order for CO concentration is 1. The order for chloride concentration is 3/2. Just for your example. Next one, the decomposition of nitrous oxide. This one. What is the rate law? The rate law is more complicated. Like this. I want to have more discussion for this one. This one is complicated, right? Complicated. This rate law is related to concentration of N2O and the concentration of concentration of O2. And this form is more complicated than this form. So let's talk about more for this one at the next slide. Okay. If you see this kind of expression, how to simplify? How to simplify? It is complicated because we have this part, right? We have this part and this part. So try to simplify this one. Okay, so the next slide. We assume two different conditions. First one, at a very low concentration of oxygen. For this case, very low concentration of oxygen. That means KCO2 is smaller than 1. Why I want to compare with 1? Because this 1, KCO2, there are two terms. So I want to compare these two terms. If this one is much smaller than this one, we can delete this one. We can ignore this one. So for very low concentration of oxygen, very low, this one is very small. So we assume it is much smaller than 1. Okay? For this case, much smaller than 1, the rate law becomes right? It's almost this one. You can simplify. So it is like the first order reaction. Also the first order reaction for N2O and for overall. In contrast, very low, we got a very low, so very high. For the condition, very high concentration of oxygen. That means this term is larger, much larger than 1, right? So the rate law becomes we delete this one. Okay. The order for O2 is -1. Order for NO2 is 1. So the order overall order is equal to 0 for this case. This way is commonly used to simplify complicated formula, especially for chemical reactions. Also, you can use this way to find rate constant. In very limited condition like very low concentration of something or very high concentration of something, you can eliminate some term to make the formula simpler. Then you can get a rate constant easier. Okay. Next one is heterogeneous reaction. Commonly, the heterogeneous reaction involving solid and gas. And commonly, it is a catalytic reaction. Like we will talk about this in chapter 10. Yeah, chapter 10. catalytic reaction. The reactant is gas. The catalyst is solid. Okay, so as shown here, in many gas solid catalyzed reactions, the rate law is written in terms of partial pressure rather than concentration. So for gas, commonly we use pressure. It is easier to express the concentration of gas. You can also use concentration of gas, but pressure is easier to obtain. So for example, I just want to show you some example in slide 13, toluene and benzene and methane. So there is a catalyzed reaction. This one combined with hydrogen, right? Catalyzed reaction, it becomes benzene and methane. For this one, so it is B, it is M, it is T, okay? So the rate of disappearance of toluene per mass of catalyst, it is minus RT plan. You will know how to write down this one in chapter 10. It is easy in chapter 10 to write down this kind of formula. You will know how to find this one in chapter 10. Okay, so I just want to show you the rate law for this reaction. Ka, capital K, KB and the KT are the adsorption constant. Okay, adsorption constant. And the unit kPa minus 1, inverse of kPa. Also, I want to show you the unit of K, but I think you can calculate by yourself. I just want to give you the answer. The unit of reaction rate should be the mole of toluene over kilogram of catalyst times second times kPa square. Okay, you can try to calculate it and find if your answer is the same as mine. If not, you can ask me. Okay.